The objective of this chapter is to try and understand or further develop our model for the atom. So we left off with Rutherford's model, which basically had a nucleus where we had our positive charge and all of our mass, and the electrons were moving around the outside of it. And we knew that this model was incorrect in terms of how the electrons were moving. So what we need to do is find out more information about the electrons and how they arrange themselves outside of the nucleus. Since we can't see them, we have to use indirect methods to understand what's going on with those electrons. Much of this evidence is going to come from the analysis of light that is both shown on substances and observing what happens, and light that's emitted from different substances. Therefore, we'll need to do a little bit with the study of light, which is going to involve some waves and a little bit of physics. So first, let's take a look at some properties of waves. So in the diagram here, we have two different waves, and some of the properties we have are the wavelength, which is the distance from one peak to the next peak. And the symbol we give to the wavelength is something called lambda. It could also be the distance from one trough to the next successive trough. So you can see that in the two pictures, the wavelengths are definitely different. The wavelength at the bottom is going to be larger than the wavelength than the one at the top. The other thing we have is the amplitude of the waves. And the amplitude of the wave, if we draw a line through the middle of the wave, a little bit. There we go. The amplitude of the wave is from that midpoint of the difference between the crest and the trough up to either the height of the crest or the depth of the trough. Okay, so either one of those would be used to calculate the amplitude of the wave. We won't use that too significantly in our studies here. And then the last one is the frequency. The frequency, if you imagine yourself standing at the beach looking down at a pebble in the water, and if you counted the number of waves that went by in a certain amount of time, that would be the frequency with which waves go by. The symbol for frequency that we're going to use, so frequency, is kind of a funky U or V shape, and it's called nu, N-U. Now, if we put the two of these together, we have our wavelength, which is the distance per wave, along with the frequency, which is the number of waves per amount of time. Okay. If we multiply these two together, we see that the wave part cancels out, and we get distance over time. And distance over time is a speed or velocity unit. So what we're going to get then is the important relationship here is the velocity of a wave is equal to the wavelength times the frequency. And so we're going to want to keep tabs on that relationship there. Now, what we think of as light is one part of a larger category of energy called electromagnetic radiation. So you can see from the diagram here that visible light is actually a very small part of this electromagnetic spectrum. And the electromagnetic spectrum is separated based on wavelength. And you can see that as wavelength gets larger, frequency is getting smaller. So wavelength is the unit on the top, Frequency is the unit on the bottom. The other thing we want to keep in mind about all electromagnetic radiation is that the velocity of all electromagnetic radiation is the speed of light. So velocity equals the symbol c, the speed of light in a vacuum, which is 3.00 times 10 to the 8th meters per second. Right? So this would be the speed of light through a vacuum. The air, our atmosphere doesn't tend to interfere with the speed of light to any great extent, so we pretty much use that value whenever we do any of our calculations involving the speed of any electromagnetic waves.